a jump, discontinuity is a jump of magnitude equal to capital P. Keyword is magnitude. If P is pointing up, dV is going to see a jump upwards. If P is pointing down, dV is going to see a jump downwards. Okay, so this is a downward jump. You're going to see these in problems. Okay, we're going to exercise these thoughts. Question: as my distance dx becomes smaller and smaller and smaller and smaller, will I see any change in the bending moment at a location where a concentrated force is acting? So this distance keeps on shrinking. Will I see any change in the bending moment as my distance gets closer and closer to 0?
No,
There will be no change because
because it's like really small. The difference is really small.
the distance is small. To create a moment, I need a distance. So force times distance is going to tend to be closer and closer to 0. So there is no change in the bending moment diagram due to a concentrated force. That's the second conclusion. And this was conclusion E. Conclusion F follows suit. Bm is bending moment value, so no change in bending moment value due to a concentrated applied force. This is conclusion F. Two more and we're good to go for a problem. So first we looked at the slope of the shear force diagram, equal to the load intensity value, negative or positive depending on the sign of the intensity. Change in the shear force is equal to the area under the distributed load. Slope of the bending moment diagram is equal to the shear force value. Change in the bending moment is equal to the area under the shear force diagram. If I have a concentrated force, I'm going to see a jump discontinuity in the shear force diagram. We will look at the problem. Depending on the direction of the applied force, it's either an upward or a downward jump. No change in the bending moment value due to an applied force. Makes sense. As I reduce the distance, there is no moment at all for this force to cause any rotations. Last one, focus on the bending moment, couple moment, I'm sorry. This is the last segment I'm going to look at. Take that and draw it out. Right here. Everything remains the same. Except now I'm going to have a couple moment. M naught. I'm going to get rid of this here. What's the sense of this couple moment? Clockwise. Very, very important, clockwise. Okay, so this is a clockwise. Couple moment. Okay. First, let's sum forces up. If I'm summing forces, if I have a couple moment, it does not do anything for me. You'll see this. V of x minus V of x plus dv is equal to 0. I'm not going to do anything in the couple moment, right? It's not going to affect my summation of forces, it's going to affect my summation of moments. And so if I look at this situation here, V of x cancels off, so I end up getting dv is equal to 0. Which tells me couple moments do not change anything in the shear force diagram. Okay, so couple moments do not affect shear force diagram, which is kind of makes sense, right? Because we said that if I have a concentrated force, it does not affect the bending moment diagram. So if I have a concentrated couple moment, it has nothing to do with the shear force diagram. It will have something to do with the bending moment diagram only. So this is conclusion G. And the last one for the day before I solve the problem. Sum of moments at any point along this little dinky piece, and you're setting the distance dx to be 0. As the distance dx tends to 0, I have this series of couple moments, they all start coagulating with each other. And so here's what I end up getting. For some moments, right side or left side makes no difference to our life. I'm going to have m of x negative. M naught is clockwise, so minus m naught. M of x plus dm is counterclockwise. Equal to 0. M of x cancels off, negative and positive. So we get the last conclusion, similar to what we had for the shear force diagram. Conclusion H. Please notice the wording of this conclusion. A clockwise couple moment, and we'll pause so that you catch up. M naught is a clockwise couple moment. A clockwise couple moment will cause a positive jump in the bending moment time. This is contrary to what we always think, right? Because we always associate counterclockwise moments with positive things. Okay, so this is different. So clockwise couple moment causes a positive jump in the bending moment time. And I'm going to write out all these findings on this panel so that we start solving problems on the remaining two. Okay? So here are what I find out. First one. dV by dx is minus w of x, where w of x is pointed in a negative y direction. Then I have v of x2 minus v of x1 is minus integral w of x dx. Likewise for the bending moment, dm by dx is v of x. Then integral m of x2 integral v of x dx. Delta v, so this is the figure. All these conclusions are based on this following figure. Delta v is equal to p with a negative sign. Delta v or dv, same thing. And delta m, change in the bending moment, is equal to m naught. For the following figure. Okay? Now let's solve some problems. Let me start with a very simple one. I have a beam, let's say length 2 meters, and A and B. I'm going to have a symmetric loading here. Say 200 newtons acting at a distance of 1 meter from each side. Draw the shear force in bending. Okay. First thing is always find the support reactions. I'm not going to do that from now on. We are done with statics in from that perspective. Please know how to find support reactions. Okay? So it is common sense. If this is 1 meter and 1 meter and the load is 200 newtons, the support reactions are evenly spaced, so 100 newtons on each side. Okay? So obtain support reaction first step. By 100 newtons pointing up, By is also the same. I'm going to get rid of this here. Okay, then comes this very sticky issue. You've got to be very patient with me as I explain this process. Okay? So I'm going to redraw that figure. Watch this very carefully. I'm going to start marking distances x. Okay, so this distance is x is equal to 0 meter. Right where the force is acting is x is equal to 1 meter. Right where the other support reaction comes up and takes its place, it's x is 2 meters. Now, if I am looking at the location x is equal to 0 meter from the left side, I'm going to label it as x at 0 minus. So looking at it from here, like how we would have left limits and right limits typically in mathematics. So I'm looking at it from the left side, it's 0 minus. If I look at a number from the right side, it's 0 plus. Okay, so if I look at it from here, x is equal to 0 plus. Likewise, look at the 1 meter from the left and the right side. 1 minus, 1 plus, and then lastly for the 2 meter as well. 2 minus, x is equal to 2 plus. Is everybody with me so far? I want to complete at least the shear force diagram for this problem, okay, before we get to the bending. Then I'm going to start saying the following. First one, so shear force diagram values. At x is equal to 0 minus, what is the shear force value? So this is x is equal to 0 is a little larger than x is equal to 0 minus. So if I'm looking at x is equal to 0 minus, what's the value of the shear force there? It has to be 0, right? There is no force there. So that's 0. Then I'm going to say, I see that there is a concentrated force which is pointing up, which means I have to use this equation right here. You notice that, right? In that equation, the force P was acting vertically down. Here, my force of 100 newtons is acting vertically up. So I'm going to see a positive jump. So I'm going to say V at x is equal to 0 plus minus V at x is equal to 0 minus. This is the change in the shear between a 0 plus and a 0 minus. This is equal to plus 100 newtons. Why is it plus? Is because this force is pointing vertically up. According to our sign convention, our results were derived in the following manner. V of x is 0 minus is 0, so V of x at 0 plus is plus 100. Right, that's 0. Next. I go all the way, so I start off at 0 plus, I'm done with the business at that side. So I go all the way and I stop short of x is equal to 1 meter. I say now I'm looking at x is equal to 1 minus. You're going to help me out now. So V at x is equal to 1 minus, minus. What's this value going to be equal to? Between 0 plus and 1 minus, what is the value of the load? Is there any load acting there?
No, 100. So
Careful, careful, careful. The 200 Newton acts at 1 meter. I'm looking at a location right before that, which is 1 minus meter. So this is going to be 0, right? Because between 0 plus and 1 minus, you see there is nothing here. Does this make sense to everybody? It's important that we understand this. The problems will get more complicated as we go on. Yes, sir, question.
Because it's the like it's this in between, like right after the 100 newtons and like right before the 200 newtons. So nothing's acting. That's why you're assuming that.
Absolutely, absolutely. So it is just stopping short of this guy. It does not include the 200 Newton force yet. Yes, sir, question.
then you just say that V of x equals the V, like that equals 100 newtons.
Sure, that's what my next conclusion is going to be. So this guy is equal to that guy, so they have to be equal to 100 newtons. Is that what you're saying?
Yeah.
Right? So I'll write this out. So V at x is equal to 1 minus is equal to V at x is equal to 0 plus, which is 100 newtons. Keep going. I'm going to get rid of this big creature here. I'm done with that. I'm going to upload this thing on Carbon so that we can consult this, or you can consult this as I solve problems. I'll upload it as a PDF. Okay. I go to the next location. V of x is equal to 1 plus. So this is D minus. What is this value equal to now?
0. Oh wait, sorry.
Negative 200. Because I'm looking at the span between 1 minus and 1 plus, I see there is this fellow which is trying to pull me down with him. This is minus 200. But V of x at 1 minus is already plus 100, so watch this. Which is minus 200 plus 100, which is equal to minus 1. Let me finish this off before we take off. Okay, I have a few more minutes. Then I go towards the end of the beam at 2 minus. Minus 1 plus. Anybody help me out here? Between 2 minus which is right before this 100 Newton force, and after the 200 Newton force, is there any force acting there? There is no force acting, so that change in shear is equal to a big zero. Yes, sir.
Is V of x equals 1 plus, is it supposed to be negative 100?
Oh yes, yes, thank you. Yeah, absolutely, absolutely. That would have derailed everything, right? Yeah. Thank you, that's my mistake. So this is 0, which tells me that V at x is equal to 2 minus is equal to V at x is equal to 1 plus, which is minus 100. And last step. You see, you always have to come back home. Home is 0. So if I look at the last difference, V at x is equal to 2 plus minus x is equal to 2 minus. Can somebody help me out here? What is this going to be equal to?
100.
Look at this. I am now sitting here, and I'm seeing what is happening in between those two locations. There is a force that is pointing up, which means that this is going to cause an upward jump in the shear force diagram at that location. So this is plus 100. V of x at 2 minus is minus 100. Minus 100 plus 100 is 0. So I end up, because there is nothing here, right? You see, there is no force acting here. So the shear force has to end up being 0 at the end of the way. So V at 2 plus is 0 newtons. One last minute while I draw this out. I'm going to remove this figure here. So shear force diagram. Which is 0, 1, and 2. 0 plus and 0 minus are very, very close to each other. So at 0 minus I'm 0, so I climb up to 100 newtons at 0 plus. So that is a climb that I see. 100 newtons. Then all the way until 1 minus I am sitting at 100 newtons positive. Immediately this 200 Newton force is causing me to jump down. As you can see, it's a negative force, and so it causes you to fall down by minus 100 newtons. So I'm sitting at minus 100. Go all the way up to 2 minus, same value. And then at x is equal to 2 plus, go back home. Alright, so we're going to take this up a notch or two in the next couple of lectures. Okay? So go back, look at these problems. I'm going to have a simple couple of problems for your homework to get you used to shear force bending moment, and then we're going to wrap it up. Thank you.